In this video, we're going to discuss polarity. So polarity is a property that makes molecules attracted to neighboring molecules. To begin with, though, we need to talk about a few trends in the periodic table. And so for that, here's the periodic table. The more in the upper right you are, so the more towards fluorine, the more electronegative you are. As you go up a column, or as you go to the right across the row, you become more electronegative. What this means is that you are able to steal, or at least are attracted to electrons more. And so the fluorine atom is more attracted to electrons than the oxygen, which is more attracted than the nitrogen, which is more than the carbon. And same going down. Fluorine is more attracted to electrons than the chlorine. The chlorine is more than the bromine, and the bromine is more than the iodine. So this is a diagonal trend. If you go from, say, phosphorus to oxygen, well, oxygen is both more up and more to the right. It is much more electronegative than phosphorus. If you go the opposite direction, though, well, you're more up to reach carbon, but you're more left. And so at that point, they're not as different. They're still a little bit different, and its exact amount different depends on what atoms you are looking at. But as you move diagonally up and to the right, you get more and more electronegative. You get better at taking electrons. Now you can look up electronegativity tables. Wikipedia has them. It'll give you values like fluorine at 4.0. Oxygen, 3.5. Nitrogen at 3.0. Carbon, about 2.5. And if you go down, chlorine would be about 3.2. Bromine, about 2.5. You could find some reasonable values. Boron is 2.0. Hydrogen is 2.1. But the actual values themselves aren't terribly important for what we're going to talk about. Just that they are different. The more different your electronegativity value, the more the electrons shared between those atoms will prefer to be on one side. So what does that mean? Let's scroll down and talk about bonding again. If we think about ionic bonding, well, let's say I had a sodium and I had a fluorine. Well, sodium, it's down here. It's actually somewhere around like 1.8. So I have something that has a 1.8 electronegativity. I have something that has a 4.0. The difference there is about 2.2. So we would say there's a delta symbol, means difference. The difference here is 2.2. If instead you had something like carbon and hydrogen, well, carbon has a 2.5, hydrogen had a 2.1 for a difference of 0.4. Well, carbon and hydrogen is a covalent bond. They actually share their electrons. Even though carbon does want electrons more, not by a lot. And so the hydrogen and the carbon are able to share fairly effectively. But with sodium and fluorine, well, they're ionic. If you ever see those two together, they're not sodium and fluorine. They're really a sodium plus and an F minus. We just don't show the charges when we write the ionic formula. If you ever actually had a true sodium atom and a fluorine atom, and they were to drift near each other, they would trade an electron. It would pop over off of sodium onto the fluoride. If your electronegativity difference is great enough, you'll just steal the electron. But if it isn't large enough, then what happens is you unequally share in your covalent bonds. Unequal sharing in a covalent bond, well, it takes a little bit of explanation. So let's go back and let's look at CH, CN, CO, CF, and we'll start with CC. No, that bond, we're just showing the one bond. The rest of the molecule, whatever it may be, we're not concerned about. We're just focused on those electrons in that bond. Well, a covalent bond says there's 2 electrons in there, but they don't really sit right between the carbon atoms. Remember that an orbital shape, your s orbital, is spherical, so a little hash grid for a sphere, right? Your p orbitals were kind of 2 spheres around the nucleus. These are 3-dimensional shapes. Your orbitals actually take up volumes. And so really, those electrons are spread out and they just happen to overlap in the middle, which is why we draw the bond there. Because they overlap in that position, they collectively spend more time between the 2 nuclei than away from it. And so the 2 nuclei can get pulled towards each other. If we average this kind of shape, then really what we have is we just have a fairly equal spread over the 2 atoms. Both carbons pull equally hard, and so they equally share their electrons. It's a nice 50-50 on both sides. What happens though when you have other atoms? Well, let's go look here at our carbon and nitrogen. Nitrogen is just a little more electronegative. And so those electrons spend a little bit more time out on nitrogen and a little bit less on carbon. Imagine holding a balloon and squeezing one side of it, and all the air kind of shoves to the other side. The result is that the electrons are a little imbalanced, and so some amount greater than 50% out on the nitrogen, and some amount less than 50% on the carbon. Think back to the sodium and the fluorine. If you completely transfer an electron, if you go all the way 100 on one side and 0 on the other, so go look back up here at our sodium and our fluoride, we've moved that electron, shared electrons 100% on the fluorine and 0% on the sodium. That left sodium with a full positive and fluorine with a full negative. As we start to push those electrons a little bit more towards nitrogen, we start to develop a little bit of charge. It's not a full negative, and so we write a delta symbol. It is a partial negative. And the carbon starts getting a little positive, but it's not all the way, so it is a delta, it is a partially positive. The result is that instead of a full positive and negative of ions, this shared system is a little imbalanced. And so you have one side that's a little positive and one side that's a little negative. But these are permanent. As far as that bond's concerned, there's always some positive and negative now. Well, if you ever had a magnet, there's a positive and a negative end. If you bring 2 magnets near each other, they attract. Same thing that held our ions together. Opposite charges attract. You can have a covalent bond that has charge on it, and that causes it to be attracted to other covalent bonds that have charge. This is polarity. Poles on a magnet, the north and the south, the positive and negative. Well, if our bond has a positive and negative side, then it has polarity. It is a polar bond. And so carbon-nitrogen has a polar bond. And we'll actually see this for carbon-oxygen as well. Oxygen is even more electronegative than nitrogen, and so it shifts even more out onto the oxygen and less on the carbon. And so it is I'll draw it as a bigger partial negative and a bigger partial positive. Because oxygen is more electronegative than the nitrogen compared to carbon, it pulls even harder. Those electrons have moved even more onto the oxygen. And so we get another polar bond between carbon and oxygen. And on carbon-fluorine, same deal. It spends the vast majority of its time and shape out on that fluorine, so it is even proportionately bigger partial negative. and a bigger partial positive. The greater the difference in the electronegativity, the greater the polarity of that bond. So, what does it mean to be polar? And what does it mean that I haven't talked about CH yet? Now, if we think back to the values, carbon was 2.5 and hydrogen was 2.1. If anything, that should slightly imbalance towards carbon. Reality, though, is that is too small a change. So the reality is they are fairly even. You have to reach a certain level before that imbalance really becomes noticeable. Let's talk about what those ranges are. If you are 0 through about less than 0.5 change in your electronegativity, then you are nonpolar. Well, carbon and hydrogen are different by 0.4. They're not different enough for a charge to really build up. It's not noticeable to any other atoms. If you are 0.5 through about 1.7 for your electronegativity difference, you are polar covalent. You're covalent. You are still sharing electrons. However, you have an imbalance in that sharing, and so charge will develop. And if you are greater than about 1.7, you are going to be ionic. And so why does sodium and fluorine make an ionic compound? Because the electronegativity difference was about 2.2, so they are significantly beyond this point. They are definitely ionic. So if we look at a couple molecules, let's look at CH4. Well, in this case, there are no polar bonds. So we're done. This molecule is non-polar. Now you notice there's two separate lines. There's a difference between a bond on the molecule being polar and the total molecule being polar, which we will see. Let's dive down and look at this example. If we have carbon to fluorine, let's do it to 4 fluorines. Well, each of these bonds is actually quite polar. So we have a significant partial negative, partial negative, partial negative, partial negative. The bonds here, there are 4 polar bonds. However, it is a non-polar molecule. Now, how can that be? How can we have polar bonds but not a polar molecule? Well, it's because the directions cancel each other out. It is pulled equally in all 4 directions and they balance one another. If you have somebody pull your left arm to the left and your right arm to your right, you don't go anywhere. You just equally get pulled in both directions. This is what's happening with the polarity on the molecule. The sum of all the bonds in all the directions and all the poles cancels out. So let's try looking at that in one that's maybe a little easier to see. Let's look at boron with 3 fluorines. And let's look at carbon with 2 oxygens. So with my boron and its fluorines, well, it is trigonal planar. Those are all 120 degrees apart. And it is flat. So there is a pole. There's definitely some significant partial negatives out on those fluorines and a big partial positive on that bromine. The result is that, yeah, I've got electron shoving out towards the fluorine. I've got them shoving out towards that fluorine. I've got them shoving out towards that fluorine. But if you think about just those directions, if you move up so much, and then you were to move this way so much, and then you were to move that way so much, Well, we effectively just ended up back where we started. If you get pulled forward, and then you get pulled backwards and to the right, and then you get pulled backwards and to the left, you end up just where you were. Now, if the angles had been off, if they hadn't been the same sizes, then maybe they wouldn't have lined up. But these are all exactly the same. They're all fluorine and boron bonds, and they're all 120 degrees apart. Now, the drawing over here is vector math. It's not part of this course. But the idea is if you sum up all those directions, they cancel out. The up is canceled by 2 downs. The right is canceled by the left. There's no net change. So boron, despite having 3 polar bonds in BF3, is a non-polar molecule. Carbon dioxide. Again, there's a significant difference between oxygen and carbon. So our oxygens are very partial negative, but that means I've got a dipole going from the center to the right, and I've got one from the right or from the center to the left. Well, if you move one direction and then you move back, you end up right where you were. This is back to the arm example. If you're pulled to the left and the right, exactly the same force, you don't go anywhere. And so carbon dioxide has 2 polar bonds, but is a non-polar molecule. So how do we get polar molecules then? Here's a lot of examples of non-polar ones. Well, let's look at formaldehyde. This is formaldehyde. In this case, I have a carbon-oxygen bond, and that is a significantly polar bond. So there's going to be some partial negative out on that oxygen. There's going to be some partial positive on that carbon. And I have 2 hydrogens that are 120 degrees apart from it, much like the BF3, except those hydrogens, well, there's not a polar bond with them. So in the end, I just have 1 polar bond going up. There's no polar bond going down to cancel it. There's no left and right. It's up only. And so this just has an overall dipole going in that direction. So this has 1 polar bond, and it is a polar molecule. If we have, let's do ammonia, NH3. I have a nitrogen. It's got a lone pair going up. It's got a hydrogen, hydrogen, and a hydrogen going down. And so this trigonal pyramidal structure, well, NH is reasonably polar, 3 and 2, 1, so a 0.9 difference. It actually puts the polarity on the nitrogen. So we're going to have the partial negative on the nitrogen, a bunch of partial positives on the hydrogens. And so my nitrogen is somewhat negative, and my hydrogens are somewhat positive. Now, if this had been boron, if those hydrogens had been flat, they would have canceled out. But because they are angled down, well, I have 3 of these. One is going in and up. Well, they're all going in and up from other opposite directions. The net result is my left and right and my forward and back cancel, but my up component of each bond doesn't. And so ammonia actually has a dipole going straight up the molecule. It passes right through the middle of all the hydrogens. If you were to do this from an above view, you'd have a nitrogen, a hydrogen, a hydrogen, a hydrogen. Your dipole is passing right through the middle, coming straight up at our face. And so there is a dipole on this ammonia. It has 3 polar bonds, but they don't cancel in all of their directions. And so this is a polar molecule. And so this is the idea of polarity. It is just compare on the periodic table where you expect the electronegativity for an element to be. If they're 0.5 or more different, then they are polar. Now, they may be more or less polar, but that's not part of what we're focusing on. They just simply are or are not polar. If they are polar bonds, you then have to look at the shape of the molecule and determine if all of the polar bonds cancel or if they are not canceled by other polar bonds. And so tetrahedral geometries like our CH4, they cancel out if all the things are the same. Trigonal planar geometries like our BF3, they will cancel out if all the things are the same, where our trigonal planar geometry for formaldehyde didn't cancel because they weren't all the same. And so that left some of our polar bonds uncountered, and so there was an overall pull on the molecule. One end of the molecule was somewhat negative, one end of it was still somewhat positive. And you have to take into account your three-dimensional shapes. And so NH3 may only have 3 atoms around it, kind of like BF3, but that lone pair means those hydrogens aren't perfectly flat and able to counter each other. They cancel their left and right, but they do not cancel their up and down. It's a little bit easier to see when you play with the model program, and so I encourage you to play around and see if you can't visualize that a little better with the PhET modeling program. Why are these important? Why do we care so much about polarity? Well, it affects a great deal of properties. And so, we'll talk more about in physical properties. The short version is, if you have something that is charged, so let's look at CF, a somewhat negative, a somewhat positive, well, there's 2 ways they could align. If another molecule nearby drifted by, and you happen to have them like this, well, my negatives would repel. They would shove away from each other, and these molecules would separate. They'd physically push apart in space and drift away. On the other hand, if your alignment was reversed, partially negative on the fluorine, partially positive on the carbon, well, opposite charges attract. That fluorine and that carbon are going to be drawn towards one another. They're not sharing electrons, they're just opposite charges. But opposite charges will draw towards each other. The net result is, as this molecule drifts around in space, if it sees opposite charge, it's going to pull in closer. They might bounce off and drift near each other and eventually get hit and float away, but they spend time pulled towards each other. This holds a material together. So polar compounds tend to hold together better. Water is a very polar liquid, and so it's very hard to break water up. It tends to hold its surface tension really well. It tends to stay together. It doesn't boil into a gas very easily. Whereas something like methane, CH4, well, it was nonpolar. Methane is a gas at room temp. In fact, larger molecules, C2, H6, C3, H8, C4, H10, C5, H12. As you make bigger and bigger and bigger molecules, the first 4 are all gases at room temp. You have to be very large before you're a liquid at room temp. Nonpolar molecules just don't hold together very well because they don't have attractions. Where a single water, OH2, which weighs almost the same amount as methane, this is liquid at room temp. That polarity that water has makes it stick to other waters very tightly, and so it doesn't break apart into a gas very quickly. And so this polarity affects a great deal of the properties of a molecule. And this is why we're interested in them.